Let's do this question first, and then we'll do some trig sub. So let's say I wanted to find the integral from 0 to pi over 3 of sine cubed x cosine squared x dx. So I'm going to do a u sub, and I'm going to pick u equal to one of those. I really don't know. Like, I don't honestly, I never remember the pattern. I really have to think about, like, okay, if I let u equal sine, my du is cosine, it's going to suck up one of those cosines, and I have one left over, which is what I don't want. So I want to let u equal cosine of x, because then my du is going to be negative sine of x dx. That'll grab one of those signs, and I'll have an even number left over, which is what I'm looking for. So I'm going to have a negative du equal to positive sine. This integral is going to become the integral of, let's say I have sine squared x times cosine squared x times sine x dx. And then this sine x dx is going to be my negative du. The cosine squared is going to be my u squared. And 1 minus cosine squared x is going to equal my sine squared x, which is going to be 1 minus u squared. To change or not to change limits of integration? My answer to that question is to usually to change, unless the change seems terrible. Meaning, like, if these numbers were not nice angles that I could take sine of easily, I wouldn't do it. But since those are really regular things to take sine or cosine of, I'm going to actually make the change. So I can see that if x equals 0, u is going to equal cosine of 0, which is 1. If x equals pi over 3, u is going to equal cosine of pi over 3, which is 1/2. So now I would rewrite this as the integral from 1 to 1/2. Yes, it is out of order. That's okay. Of 1 minus u squared times u times a negative du. And I always like to take the opportunity to, if my integral is written out of order and I have a negative sign out in front, it really feels like it might as well just change the order and make it positive. So I would rewrite this as the integral from 1/2 to 1 of u minus u cubed du. Then we integrate, we get u squared over 2 minus u to the 4th over 4 from 1/2 to 1. And the whole benefit of having changed our limits of integration is that we don't have to go back and plug in u equal to cosine and then plug in 0 and pi over 3. So we're just going to plug in 1. We're going to get 1/2 minus 1/4. Then we're going to plug in 1/2, and we're going to get 1/4 over 2 minus 1/16 over 4. And yeah, we could simplify that, but we don't need to, right? You can simplify that on your own. So yeah, looks good. So I just want to kind of show one where we had actually limits of integration with this u substitution. I like changing limits of integration most of the time. Let's go ahead and move along. Yeah, let's do, actually, I had one more example I want to look at, which is the following thing. So sometimes this other type of thing comes up that I wanted to make you all aware of, which was the integral I actually started right, but then I felt like I should do something different first. The integral from 0 to pi over 3 of the square root of 1 plus cosine of 6x. Yes. Yeah, oh yeah, go ahead. Yeah.
Isn't it going to be u squared? A u squared times because cosine is squared and our u is.
Oh, good call. Yeah, I missed that completely. So that means this is incorrect. We should have had would have been the integral from 1/2 to 1 of u squared minus u to the 4th, which would then be u cubed over 3 minus u to the 5th over 5 from 1/2 to 1, which would then be 1/3 minus 1/5 minus 1/8 over 3 is 1/24, and 1/32 over 5 is 1/160th. lots of practice and tricks. Really, I mean, when I want right, what I really did was 32 times 5 is really 32 times 10, and then divide by 2. Multiply by 5, multiply by 10, divide by 2. It's much easier, I think. Anyway, lots of fun tips and tricks. If you want to talk about multiplying things sometime, I'm happy to. So for this squared 1 plus cosine of 6x, to me, this one never looks obvious, but you might see kind of part of the trig identity for cosine squared. If you think about it, cosine squared of theta is equal to 1 plus cosine of 2 theta all over 2. So if we let theta equal 3x, then this is going to be 2 times 3x. And so we can say that 2 times cosine squared of 3x is equal to 1 plus cosine of 2 times 3x. And that's going to be a lot easier to deal with. So I'm going to rewrite this as the integral from 0 to pi over 3 of the square root of 2 times cosine squared of 3x. And here's where we actually have to be careful because it's a definite integral. We can't just say it's equal to the square root of 2 times cosine of 3x, or the integral of that. Because since you have the square root of cosine squared, we really have the absolute value of cosine of 3x. So let's write this down here. Yeah. So what we really have here is that I'm going to bring out the square root of 2 and just say the square root of cosine squared of 3x is equal to cosine 3x if it's positive, and it's equal to negative cosine of 3x if it's negative. Just like a regular absolute value, right? The absolute value of x is x if x is positive, and it's negative x if x is negative. So the problem here is that between 0 and pi over 3, well, if you look at cosine of 3 times 0, that's equal to cosine of 0, which is 1. But cosine of 3 times pi over 3 is cosine of pi, which is equal to negative 1. So somewhere between 0 and pi over 3, we're switching from positive to negative values. And really it's halfway between, because what we're really doing here, right, if our angles need to multiply by 3, we're kind of going from 0 to pi, and halfway between that, in the middle of the first and second quadrant, pi over 2, or pi over 2 divided by 3, which is pi over 6, is where it's going to change. So what we have here is that this is going to really equal positive cosine if our angle is is less than pi over 6, bigger than 0, and it's going to be negative if our angle is bigger than pi over 6 and less than pi over 3. So what we're going to do is we're going to break this in. Not what we're going to do. What we have to do is break this integral up as, let's pull the square root of 2 out in front, and then write it as the integral from 0 to pi over 3 of cosine of 3x plus the integral from pi over 3, pi over 6. Pi over 6, to pi over 3 of negative cosine of 3x. So sometimes when you have a square root of a trig function squared, you do have to do this thing where you think about it really being the opposite value. It's really only super important when you have a definite integral, because that's where you actually might see it being sometimes negative or sometimes positive. So then we're going to do this. We're going to get, let's see, the antiderivative of cosine of 3x is sine of 3x over 3 from 0 to pi over 6. And then we're going to get negative sine of 3x over 3 from pi over 6 to pi over 2. Pi over 3. Oh my gosh, can I write the right numbers? Maybe. So then plugging this in, what do we get here? Sine of 3 pi over 6 is sine of pi over 2. So 1/3 minus sine of 0 is 0/3. Plus, and then if we plug in pi over 3, sine of pi is 0. We plug in pi over 6, we get minus sine of pi. 3 pi over 6 is pi over 2, so 1. To end up with square root of 2 times 1/3 plus 1/3. So we get 2√2/3. But if we had done this incorrectly, we would have gotten an answer of 0. So if you just said that this was the integral from 0 to pi/3 of the square root of 2 of cosine of 3x, you would have gotten square root of 2 times sine of 3x/3. And then when you plugged in both endpoints, you would have gotten zeros. And that is not correct. Which makes sense, right? Because this function here, this square root of 1 plus cosine 6x is definitely always positive. And if the function is always positive, the area under it should certainly be non-zero. This was not different. It really kind of depends on what you're doing. Like technically the correct answer is to write 2 absolute value of cosine of 3x, but people often get a little wavier when it's indefinite. So it really kind of depends on what you're trying to achieve. Most of the times we would probably just ignore the absolute value if it were indefinite. Maybe not with good reason, just because that's what people typically do. Okay, so those were just a couple examples I want to show you all. But let's go ahead, unless there's questions about this. Let's go ahead and change, well, not change gears, continue on in a higher gear and talk about trig substitution. So trig substitution, one of my favorites. So trig substitution is kind of almost the opposite of u substitution in that you're not setting u equal to some piece of the function in the integral. You're setting x equal to some trig function and then replacing all the x's with that trig function. And here's kind of the guidelines. So I'm going to remind you all of some trig identities. 1 minus sine squared theta is equal to cosine squared theta. 1 plus tangent squared theta is equal to secant squared theta. And secant squared theta minus 1 is equal to tangent squared theta. Now, I know those last two are really the same, which is totally fine. But the reason that we keep these all in mind is because they're going to tell us that we with 2 e's, sure. If we see 1 minus x squared, we're going to let x equal sine theta so that we can get this trig identity to show up. And if we see 1 plus x squared, we're going to let x equal tangent theta. So we get this trig identity to show up. And finally, if we see x squared minus 1, we're going to let x equal secant theta. Now, there's actually a more general version of that, which we'll talk about in a few minutes here. But that's kind of the idea. The other thing I want to point out, because I think it's just cool, and not just cool, I think it's actually useful and cool, is that if you think about the inverse trig functions and their derivatives, these relationships are exactly there. What I mean by this is the derivative of the arc sine of x has a 1 minus x squared in it. And the derivative of the arc tangent of x has a 1 plus x squared in it. And the derivative of the arc secant of x has an x squared minus 1 in it. Absolute value there sometimes, depending on how you learned it. But the point is that if you know these inverse trig derivatives, you can remind yourself of what you're looking for to use that trig function. So when I see 1 minus x squared, I'm like, oh, derivative of arc sine has a 1 minus x squared. That means I should use sine if I have a 1 minus x squared I'm trying to do a trig sub for. I know it's kind of a convoluted path to get there, but it totally works. So let's look at an example that doesn't require this. Let's say I want to evaluate the integral from 0 to 3 of the square root of 9 minus x squared. Well, we don't need trig substitution to do this because we have geometry. So with geometry, we can say, well, that's part of a circle. That's just the top right quarter of a circle of radius 3. So that integral is equal to, well, let's see, it's going to be 1/4 of pi times 3 squared, or 9 pi over 4. which is nice to see, so that now when we do it using trig substitution, we will be sure that our answer is correct. So we're going to use trig sub. Now this one's a little different than what I've kind of said, because I don't have a 1 minus x squared, I have a 9 minus x squared. I'm still looking to make that same kind of trig identity show up though. So the idea here is going to be, I want to get a 1 minus sine squared. So I'm going to let, it's done again. Instead of letting x equal to just sine theta, we're going to let x equal to 3 times sine of theta. The reason for that being that if we actually plug that in there, we're going to get 9 minus 3 sine theta squared, which will be 9 minus 9 sine squared theta, which will be 9 times 1 minus sine squared theta. So that's the idea, is you're always trying to get that trig identity to show up, or one of the trig identities to show up. Okay, so we're just going to do it. We've got x equal to 3 sine theta. We also need dx. So dx is equal to 3 cosine theta d theta. I want to emphasize here, when you're doing a trig substitution, it's vital that whatever your variable is to start off with, usually x, that you pick x equal to whatever your trig function is of pick anything other than x for your variable, typically theta. But don't say that x is equal to 3 sine x, because you have to make sure that this dx changes into what it's equal to, which is all of this. So when we rewrite this, we're going to rewrite it as the integral of the square root of, well, so you can kind of do as much work or as little work as you want to in here. I'm going to go ahead and write it as this, because I know that I'm going to show all the work. I lied. I'm going to write it as 9 minus 3 sine theta squared. And I'll multiply it by my dx, which is my 3 cosine theta d theta. Do we want to change limits of integration? That's a good question. Do we? I kind of do. Yeah, so let's go ahead and change them. So it's actually kind of weird to change them though. Right, so if we have x equal to 0, that's going to be 3 sine theta equal to 0. So then you have to think about what angle you take sine of to get 0, which is 0. And if x equals 3, we've got 3 sine theta equal to 3, which means sine of theta equals 1, which means theta is pi over 2. We also probably could have worked it out just thinking about the fact that if you've got that first quarter of the circle, it makes sense that your angle is going from 0 to pi over 2 from the graphical perspective. Questions? Time?
Yes, please.
Oh, sure. Yeah. So we're just going to do a little bit of simplifying now. So the whole point, oh my gosh, what's my looking for? The whole kind of there's a word, like, well, the words escape me more than ever now. Is the whole kind of reason we decided to make this choice in the first place was because we want to get rid of that square root. We want to make a choice for our x so that we're able to get something nice that's just something squared. And the whole idea is that this 1 minus sine squared is going to become cosine squared. So we can rewrite this as the integral from 0 to pi over 2 of the square root of 9 is 3, and the 1 minus sine squared becomes cosine squared. And then the square root of cosine squared is cosine, because we're between 0 and pi over 2, so we're totally fine. We're in the first quadrant where cosine is positive. So we have 3 times 3 is 9, integral from 0 to pi over 2 of cosine theta times another cosine theta. And now we're going to use the trig identity for cosine squared, which is 1 plus, cosine of 2 theta all over 2. I would bring out the 1/2. And then finally, we can integrate these parts and get 9/2 times the integral of 1 is theta. The integral of cosine 2 theta is sine 2 theta all over 2 from 0 to pi over 2. We plug in, so we get 9 over 2 times pi over 2 plus sine of 2 times pi over 2 is sine of pi, which is 0. Fun fact, something I see all the time. When you do these integrals and you've got a sign, a lot of the times it's going to equal 0. Because a lot of the angles you end up plugging in end up being a multiple of pi after you multiply them by whatever. Minus, when we plug in 0, we get 0 plus sine of 0 is also 0. So we end up with 9 times pi over 4, which is exactly what we said the answer should be. Which is great. Then you, if you really want to, you can say like, maybe I only want like, well, if you wanted to go like from 0 to like 3/2, you could find out how much area was like in this part here. We're not going to do that right now, but it's kind of neat to think that you can kind of get other weird sections of a circle now that are not just normal like pieces of pie. Kind of cool. So questions about any of what we've done here so far? So I'll reemphasize there's a word, I can't find it. The thing that makes us want to do the thing. There's a word for that, right? Where you like, you see a thing like, oh, it's there. Not the criteria. The motivation, yeah, that's probably good enough. The motivation, sure, yeah. That's not quite it, but it's good. The motivation for this is that we're trying to make it so the inside of the square root turns into a trig. It's always what we're trying to do when you're thinking trig substitution. I should back up though and say trig substitution, like partial fractions, which we haven't talked about yet, are what I typically refer to as methods of kind of last resort. You should look for other things first. You should look for a U sub first. You should look for a U sub with a back sub first. Yeah. Integration by parts, usually, although usually you're not considering, like this kind of problem isn't one where you really look for integration by parts because it's not a mixture. But this is kind of something you don't try until you've probably at least thought of trying other things. Let's look at more examples. So let's say I want to try this one. The integral of dx over x times the square root of 25 minus x squared. So again, I see a something minus x squared, a 1 minus x squared, or a 25 minus x squared. That means I'm going to pick sine again. Sine is my trig function here. So here I'm going to let x equal 5 times sine of theta. Because then my 25 minus x squared will become 25 minus 25 sine squared. And I can factor out the 25. Great. So let's do that. Oh, I have to also find dx, right? So make sure you write down what dx is as well. So dx is going to be 5 cosine theta d theta. Yeah. So if I were really like doing this, like if I was taking a test, I would probably write all this down on the left. I'd be like, okay, x is 5 sine theta, 25 minus x squared is all this. And I would probably continue this on all the way to this is 25 cosine squared theta. So that when I take this in my integral, I can just replace it with this. I feel like that's worth doing. You might do one step first. You might first write this as, oops, I wrote dx twice. Sorry, silly. So my dx is my 5 cosine theta d theta. And my x is 5 sine theta. And my square root is the square root of, I'm going to start off with 25 minus 5 sine theta squared. just so that the person reading my work knows that I have actually put in 5 sine theta for x. They recognize that I know what I'm doing. It's replacing every x with 5 sine theta and the 1 dx with 5 cosine theta d theta. And then I'm going to be like, well, I did all the simplifying over here, so I can just go straight to saying that it's going to be the integral of, let's cancel a 5, cosine theta over sine theta times the square root of 25 cosine squared theta. Right? I just replaced my 25 minus 25 sine squared with 25 cosine squared because of the trig. And then I'm going to simplify that. The whole point of getting that in there is now that square root is manageable. I can get rid of it because the square root of 25 is 5, and the square root of cosine squared is cosine. And yes, this is one of those examples where we're just like, yeah, I don't know if it's positive or negative, so I'm not worrying about it. I'm not worrying about the absolute value of cosine theta. I'm just saying it's cosine theta. Simplify as much as possible. So now we have 1/5 the integral of 1 over sine, also known as cosecant theta. Last class, we did talk about the integral of cosecant theta. It's probably something you're eventually expected to memorize, probably. And I'm curious which way you granted. Oh yeah, we gotta do that too. Cool, sure. So there's 2 valid formulas for cosecant. I prefer this one. It's the positive natural log of the absolute value of cosecant theta minus cotangent theta.
Is there normally a negative sign in front of the?
Or I should say the or is normally, there's not a normally for this one because both versions are considered totally valid and normal. So, but the other valid version of this is you can say it's negative 1/5 natural log of the absolute value of cosecant theta plus cotangent theta. So instead of having a minus sign here, you have a minus sign up front. The reason this is true, literally, is because, let me just show you, because I think people are often confused about this, and they're like, why is that this is true? It's really because if you take negative natural log of the absolute value of cosecant of theta plus cotangent of theta, and you bring that negative one up as a power, you have the natural log of the absolute value of cosecant theta plus cotangent theta to the -1, which then just becomes the natural log of the absolute value of 1 over cosecant theta plus cotangent theta, which is really equal to the natural log of, well, cosecant is 1 over sine, cotangent is cosine over sine. And if we get the common denominator here, we can write this as the natural log of the absolute value of 1 over 1 plus cosine over sine, which is really the natural log of the absolute value of sine over 1 plus cosine, multiplied by the conjugate 1 minus cosine. And then we end up getting the natural log of sine times 1 minus cosine, all over 1 plus cosine times 1 minus cosine is 1 minus cosine squared. That's really sine squared. Cancel a sine. And then 1 over sine is cosecant. And cosine over sine is cotangent. And it's minus. And that's why they're the same. Yeah.
Cosecant, whereas we say like sine as sine and then cosine is a co of sine. Like we put the co after the sine for cosine, but when it's a reciprocal, we do the opposite.
There are reasons for the names, like, yes, there are reasons why people have named them the way they're named. And it's a whole, we can get into that some other time. But yeah, but the way I was thinking about it is basically you want each reciprocal pair to have one cofunction and one non-cofunction. That's why sine goes with cosecant, cosine goes with secant, and tangent goes with cotangent. So that each reciprocal pair has one co-function and one not co-function. Anyway, so yeah, you can use either one to answer your question. Back to what we were doing though. So here's what I think is kind of the funky part about these. If it's indefinite, we started with x's. We need to end with x's. So how do you turn this back into something with x as well? The key is looking at your choice for your trig substitution in the first place. So take your trig substitution. And typically it makes sense to isolate the trig function. If it's just x equal to sine theta, then I would write sine theta equals x over 1. Here I'm going to write sine theta equals x over 5. And I'm thinking of x as the opposite and 5 as the hypotenuse. And here's the great thing about this. I'm going to draw a triangle. And in my triangle, there's theta. And x is the opposite and 5 is the hypotenuse. And here's what's super cool about this every time. We always want to find the third side of this triangle, but the third side of the triangle is always going to be the square root in the integral that made us do the trig sub in the first place. Meaning, I know without even thinking about it, that the third side of my triangle is definitely going to be the square root of 25 minus x squared. You can also use the Pythagorean theorem to find it, but it's the same thing. You're going to get the square root of 25 minus x squared. So then, looking at our thing here, our answer, I'm going to get 1/5 natural log of the absolute value of cosecant of theta, which is the reciprocal of sine, so 5 over x, minus cotangent of theta, which is the reciprocal of tangent, so not opposite over adjacent, but adjacent over opposite. So square root of 25 minus x squared over x. Let's see. And yeah, you could write that as one fraction, I suppose. So you write it as 1/5 natural log of the absolute value of 5 minus the square root of 25 minus x squared all over x. We'll see. Or negative 1/5 natural log of 5 plus square root of 25 minus x squared all over x. So that to me is always kind of the interesting part. Well, one of the interesting parts about doing these trig substitution problems is you have to then go back and figure out how to write x or theta in terms of your x's. Let's look at some more.
Thank you, James.
You're very welcome. Good luck on your test. Yeah, do some more. Something here? No. Again, if you have questions, don't hesitate to slow me down. So let's look at this one here. By the way, so I should point out the more general kind of way of thinking about trig substitution is for trig substitution. If we see, instead of saying 1 minus x squared, we typically say like a squared minus x squared. Then we're going to let x equal a times sine of theta. Or if we see a squared plus x squared, we're going to let x equal a times tangent theta. Or if we see x squared minus a squared, we're going to let x equal a times secant theta. So that we get the trig in. So let's look at this next one. The integral of 1 over x squared times the square root of x squared plus 16. I should mention, although you don't often see it, someone could totally do this question as like, so just a quick point here. We're going to let x equal 4 tangent theta here. I also remember that the plus looks like a T. And so whenever I see a plus sign between the two things, I know it's going to be tangent because plus looks like T. But I should just mention, I could have asked the question this way. 1 over x squared times the square root of x squared plus 5. And that would still be a trig sub. It's just a little less nice. Here, the trig sub would be x equal to the square root of 5 times tangent of theta. It's totally valid. It's just less often seen that way because it's a little bit messier. But it's the same work. It's just here your square number is not really a nice square number. But we're still going to do the same sort of thing that we would if it was 25 or 16.
If we're gonna do like more like a U sub thing and in that example on the side.
Well, so this, I'll point out, this example on the side is virtually the same as this example here. I've just changed 5 with 16.
If the x squared in the denominator wasn't there, would U have to equal 4?
So if the x squared wasn't there,
Yeah.
I would still do a trig sub. Yeah,
Because if you had a U sub, you need to have.
right,
An X.
right. So I'll point out that if instead you had this integral, the integral of x over the square root of x squared plus 16. While you should not do a trig substitution, here is where you would want to do a u substitution. You would let u equal x squared plus 16, and your du would be 2x dx, and so 1/2 du would equal x dx. And this would exactly work out as we'd have the integral of 1/2 du over the square root of u, which would be the integral of 1/2 u to the negative 1/2, and then it would be pretty straightforward.
I'm just forgetting about
Sure.
integrals of arcsine and arctangent.
So here's the thing. If you had, so you actually don't have to really have those memorized if you know how to do trig substitution. So for example, I'm gonna do this one on the next page. For example, if someone said, I want you to integrate 1 over, oh gosh, now I'm gonna sure x squared plus 9, you could remember that that's an arctangent thing, and it's going to be sure 1/3 arctangent of x over 3 plus c. But you could also do it using trig substitution if you didn't memorize it. You could let x equal 3 tangent theta and go through the whole process. In a similar way, if I was going to, now, again, do I want to do all that work? No, I want to have it memorized. But could I do that work? Sure. In the same sort of way, if you saw something like the integral of 1 over the square root of 1 minus x squared, someone's asking you this question, they're expecting you just to give them the answer arcsine of x. But if you didn't remember that the answer was arcsine of x, you could totally do the trig sub and let x equal sine of theta. And that would get you there eventually. In fact, let me show you because I think it's kind of neat. So if we were faced with this integral here and we forgot that it was arcsine, so we would let x equal sine of theta, our dx would be cosine of theta, d theta, and then we start replacing things. This is going to become the integral of 1 over the square root of 1 minus sine squared, and then our dx is cosine theta, d theta. But then 1 minus sine squared is cosine squared. So you have the integral of cosine theta d theta over the square root of cosine squared. But that's just the integral of cosine theta over cosine theta, which is just the integral of 1 d theta. And what's the integral of 1? Right. Theta plus c. But now what's theta equal to? Well,
X is equal to sine theta, and theta would be x sine theta.
exactly. Which actually brings up a good point. If theta on its own shows up in your answer, you need to write it's the arc trig function of whatever, or whatever trig function you use, it's the arc trig function of x. Cool. All right, let's go. So let's go back to that other problem answer with it. Do I have enough room here? Not really. Sure. So I was looking at the integral of 1 over x squared times the square root of 16 plus x squared dx. I think I'd written x squared plus 16, but it doesn't matter. And again, just back to your points, you see that yes, you should look for the u sub first. So I would definitely think about, oh, is u equal to 16 plus x squared a good choice here? No, because my du is 2x dx and I don't have a 2x dx. But it's still good to make sure we think about it before we just blindly go on with our trig substitution. But now I'm going to go on with my trig substitution. So I'm going to let x equal 4 tangent of theta. And my dx is going to be 4 secant squared of theta d theta. So then when I start throwing things in here, I'm going to have the integral of 1 over, so x squared is going to be 16 tangent squared theta times the square root of 16 plus x squared, which is 16 tangent squared theta. And then my dx is equal to, I might just write it on top, 4 secant squared theta d theta. Once again, the whole point of doing this trig substitution is so that we can see now that the inside of that square root is going to simplify this. It's just something squared. So 1 plus, so I can factor out the 16. So let's do some simplifying here. So cancel a 4. And now I'm going to pull out that 1/4. And I have a secant squared theta on top. I still have a tangent squared theta on the bottom. And I also have the square root of 1 plus tangent squared times 16. Sorry, I forgot the 16. So the 1 plus tangent squared theta is going to become secant squared theta. So then we're going to rewrite this integral as 1/4 the integral of secant squared theta over tangent squared theta times 4, because the square root of 16 is 4, and then the square root of secant squared is just secant. Cancel a secant, and we're left with, and bring out a 1/4, 1/16 the integral of secant theta over tangent squared theta d theta. Which seems terrible. Yeah, it seems really terrible. You can do that. That's terrible though. So I don't see a good U sub at this point. So I would go to my next kind of go-to if I've got trig functions and I don't know what to do with. If I don't see a nice U sub, I'm typically going to then start writing things in terms of sines and cosines. So I'm going to rewrite this as 1 over 16. I've got the integral secant is 1 over cosine. And tangent is sine over cosine. So I've got sine squared over cosine squared. We should definitely flip and multiply. So we've got 1/16 times the integral of 1 over cosine times cosine squared over sine squared. Cancel the cosine. And you've got 1/16 the integral of cosine theta over sine squared theta. There's actually 2 ways to go here. I'm going to show you the more normal way. The more normal way of doing this is to see that there's the U sub at this point. We can let U equal sine of theta. So we let U equal sine of theta, or du is going to be cosine theta, d theta. So this is going to look like 1/16 the integral of du over u squared. Or if you prefer, 1/16 the integral of u to the -2 du. Which ends up becoming 1/16 times u to the -1 divided by -1, which is times -1. Let's see. And then plugging back in what u is equal to, I've got a negative 1/16 sine of theta to the -1. And nobody's writing sine of theta to the -1. What should we write instead? Cosecant theta, right? Sine theta to the -1 is just cosecant. So really what I have here is negative 1/16 cosecant of theta plus c. Now something I want to point out, because I think this is probably worth seeing, you can actually see a different way of getting there. If you had written this integral of cosine over sine squared as 1 over sine times cosine over sine, which is really cosecant times cotangent, you might recognize that the antiderivative of that is negative cosecant. So it's maybe a faster way to get there, but I feel like you kind of have to see the thing to be able to do that. We're not done, because if you're doing an indefinite integral, you have to end with the variable you started with. So we have to go back to x's. And so for trig substitution, that's always doing the triangle thing. I should say it's not always doing the triangle thing. Some people like to say you use a trig identity, but it's easier if you just draw a triangle. So let's see. Here's my relationship between theta and x. So I'm going to say that tangent of theta is equal to x over 4, which is opposite over adjacent. So my triangle, there's theta, there's x, there's 4, and the third side of my triangle should be the square root of 16 plus x squared. So then if I want to find cosecant of theta, it's going to be the reciprocal of sine. Sine would be opposite over hypotenuse, so cosecant hypotenuse over opposite. So I'm going to get -1/16 times the square root of 16 plus x squared over x plus c. That part always feels kind of the funkiest to me. You're like, oh, I've gotten to theta, but then I have to go back to x.
Forget that.
Right. So whenever you're doing this, like, if it's indefinite, you're like, oh yeah, I have x's, I need x's at the end. You always want to draw this triangle. Let's see, do I have another example? I definitely have one example. Yeah. We have time. Yeah, sure. Let's find a better one. We don't really have time. I want to do more, but we don't really have time for more. It'll take too long to do more. Let me just say one thing here. Oh, I know what it is. Yeah. So let me show you one more thing just to kind of point out one thing. So let's say we had the integral of x cubed over the square root of x squared plus 1. This problem can be done with the trig sub. You could totally let x equal tangent theta. You can also do this with a u sub and a back sub. Typically, I think that's probably easier. Let me show you. Yeah, we can do that in 2 minutes. So we let u equal x squared plus 1. My du is 2x dx. And I guess I'll do it you guys like to do it where you like divide and just get dx by itself. Is that a thing? No, I'm thinking my other class. Sorry, I'm not. So if I was doing this, I'd be like, okay, well, 1/2 du is x dx. And I'm going to rewrite this integral in a way that breaks off an x from my x squared. And then still leaves me with a square root of x squared plus 1 on the bottom. So my x dx is giving me my 1/2 du. My x squared plus 1 is giving me u. And solving for x squared, I'm going to say x squared is equal to u minus 1. So that's what this part here I'm going to back sub in for is. So writing this out, I've got a 1/2 that's going to come out in front. I've got a u minus 1 on top and a square root of u on the bottom. I can simplify that. U divided by the square root of u is the square root of u. 1 divided by the square root of u is u to the negative 1/2. And then we can anti-differentiate and get 1/2 u to the 3/2 times 2/3 minus u to the 1/2 times 2 plus c. And then we can distribute the 1/2 and also plug back in u equal to x squared plus 1. So distributing the 1/2, we get 1/3 x squared plus 1 to the 3/2 minus 1 times x squared plus 1 to the 1/2. Let's see. That's probably easier than doing the trig substitution. It also depends on how you feel about it. Like maybe you really like trig substitution. You're like, yeah, trig substitution all day long. But this is probably the easier way to do it. So again, I'll say definitely look for a u sub before you start doing trig substitution. That's really kind of the only method that will usually be plausible if it's a type of trig substitution problem. Maybe you can do a U sub. If you can't, that's probably a trig sub. All right. The only other thing I'll say about trig substitutions is with rare exception, every trig substitution is going to have a square root or some 1/2 power. It might be a 3/2 power or a 5/2 power. Usually it's just a square root of either something minus x squared or x squared minus something or something plus x squared. There is kind of one exception to this where it's not a root, but that's kind of it. So if you're thinking trig sub, you should be looking for a square root of x squared plus 1 or 1 minus x squared or x squared minus 9 or something like that.